Let's start this class then. अच्छा, पिछली क्लास के अंदर we studied all of our types of decays. हमने बीटा, अल्फा और गामा रेस के properties पढ़े थे. And where we left off was our count rate or our rate of decay. ठीक है? Now, count rate or rate of decay is a very important concept for this chapter because इसके आगे it builds on a lot of the things जो हम आगे पढ़ेंगे. अच्छा, count rate or the rate of decay basically just refers to the number of radiations emitted per unit time. हमने कल पढ़ा था that unstable nuclei they emit radiations in order to mimic the isotope that is more stable. So हमने पहले ये lithium की example देखी थी where we saw that Li7 was this stable isotope and both of these other isotopes want to mimic this isotope, the Li7 one. So they somehow want to become like the Li7. So what they do in order to mimic this Li7 is to emit radiation so that they can have the same properties of Li7. So taking example of Li8, Li8 wants to lose a neutron so that it can become very similar to Li7 because it has one more neutron than Li7. And Li6 wants to gain a neutron. Okay? So that is why radiation basically happens. And the count rate over here, this one, the count rate is simply the number of radiations in a given time. Okay? This is your formal definition that you will probably have to write in your exams, this one. But in actuality, अगर हमने समझना है, the count rate basically, or the rate of decay, basically just tells us how quickly an element starts to decay. Okay? How quickly it is undergoing decays of either alpha, beta, or gamma, how quickly it is emitting radiation. Okay? Now, जो आपका count rate होता है, it is directly proportional to the number of unstable nuclei in a given sample. ठीक है? So if I were to show this to you guys, let's say मेरे पास initially है, I'll draw a few circles over here. These blue ones are currently unstable nuclei. Okay? So I have a lot of unstable nuclei currently. Now I told you guys that after radiations, unstable nuclei turn into stable nuclei because they, after the radiation has happened, they've turned into more stable nuclei, right? So after a given amount of time, let's say मैं कोई 2-3 सेकंड वेट करता हूँ, ठीक है? After I've waited 2 to 3 seconds, what is going to happen is some of these unstable nuclei, the blue ones, they are now going to undergo radiation and they're going to emit whatever decay process they're undergoing, and now they're going to become more stable nuclei. So you make gray se jo kaat raha hu, these are now molecules that are stable. Now your rate of decay or your count rate is actually directly proportional to the number of unstable nuclei in a given sample. Okay? This is to say that if your sample, let's say, has these many unstable nuclei, as it undergoes radiation, your unstable nuclei actually convert into stable nuclei. So over time, you'll see that the number of unstable nuclei that you have in a given sample size actually starts to decrease, right? Because again, they're undergoing decays, and because of these decays, they're going to start turning into stable nuclei. So the total number of unstable nuclei over time actually starts to decrease. Now, how does this actually affect your count rate? Well, over time, since it is proportional to the number of unstable nuclei, the count rate would also start to decrease, right? So after a given amount of time, let's say these three are now stable nuclei because they've undergone radiation. Now I only have about, let's say, 7 of these nuclei. So the count rate of these 7 nuclei is obviously going to be lesser than the count rate that I had with 10 nuclei that I had before originally. So that is why, as decays happen, as radiation is emitted, the count rate over time often tends to decrease, as we'll also see in the next section. But any questions so far with regards to this?
No.
No? Okay, sure, that's good. So basically, the same process, okay, the count rate tends to just decrease over time. Okay, now let's move on to perhaps one of the most important concepts of this chapter, half-life. Okay? Half-life is simply the time taken for the number of radioactive nuclei in a sample to halve. Okay? So let's say if I had, in this example, I had 10 radioactive nuclei in the start, right? It's gonna be let's say, well, yeah, I'll just make it 8 for now, right? Mm, Let's make this 8 for now. Now, half-life is basically just the time taken for the number of unstable nuclei to halve. So currently, I have 8 unstable nuclei over here. Now, after a certain amount of time, as I told you guys, the number of unstable nuclei are going to be converted into stable nuclei through radiation, right? So after a certain amount of time, I'm actually going to just be left with 4 unstable nuclei, right? Because the other 4 are now stable nuclei because they've undergone radiation. So because of this reason, the amount of time taken for 4 of these, unstable nuclei to turn into stable nuclei, or the number of unstable nuclei to basically halve in their amount, is the half-life. I'm just going to write H over here to denote that. Okay? Now, this is one half-life. This is to say that in one half-life, the number of unstable nuclei has now halved. Now, if this were to undergo another half-life, the amount of unstable nuclei over here have to halve, which just basically means half of these nuclei have to be transformed into stable nuclei. So in the second half-life, the number of unstable nuclei that I will have left will be 2. Now in my third half-life, this is going to be 1. Okay? So basically, half-life just tells us the amount of time needed for the number of unstable nuclei to halve. So with every single half-life, your unstable nuclei are simply going to be continually halving in their amount because half of them are still unstable and half of them are now being converted into stable nuclei and they have already undergone radiation. Okay? And this is the graph for half-life. Also, one other thing. Okay, I'll tell you this in the next slide. But basically, this is just the graph, a general graph of half-life. And it always sort of resembles this shape, okay? So on the right, we've discussed this so far, which is the number of nucleides. This basically, this T half, right, this symbol, just basically means half-life, okay? So for now, just this is your half-life. And you can see that initially we had 1,000 nucleides, right? 1,000 into 10 raised to power 3 nucleides, because our y-axis is the number of nucleides over here. And T half basically is your half-life. So you can see at one half-life, this T half is your one half-life. Your number of nucleides over here were originally 1,000, and at one half-life, your nucleides have now halved. Now they're at 500. Make sense? At the second half-life, this 2 T half, T half just is basically half-life. So at your second half-life, originally you had 500, now you have 250. So again, 500 to 250, they've halved. And at the third half-life, you have 250, say, 125, and they've also halved. Okay? So with every single half-life, your just number of nuclei are continually just halving again and again. Okay? Now, remember how I told you guys before this that the count rate actually depends on the number of unstable nuclei, right? So as time passes, if the number of unstable nuclei start to decrease, your count rate also starts to decrease by the same amount, you could say, because they're proportional, right? So if my number of unstable nuclei actually halves, then by that logic, since count rate is proportional to my unstable nuclei, the number of my count rate is also going to start halving with every single half-life. Okay? So these number of nucleides over here actually represent the number of unstable nucleides in your given sample, right? Now, I told you guys that after every single half-life, these number of nucleides are going to halve, right? If I were to plot a graph of the counts per minute or the count rate, this is a fancy way of just saying the count rate, right? This is just it is sort of going to undergo the exact same shape, right? Because with every single half-life, let's say my half-life in this case is 2 days, right? My count rate is also going to start halving with every single half-life because my count rate is proportional to the number of unstable nuclei I have, right? If after a given time these unstable nuclei are halving, then my count rate is also going to halve in that same amount of time. So if in 2 days, instead of writing it, I'll just tell you guys, if in 2 days the number of nuclei are going to halve, then the count rate by that same logic is also going to halve because my count rate is proportional to the number of unstable nuclei that I have, right? So by that logic, we can also plot a counts per minute graph, or you can have a number of nuclei graph that can show up in your exams. They can also put a mass of sample, mass of radioactive sample, mass. They can put the mass on the y-axis as well. But basically, the logic still remains the same, right? That with every single half-life, whatever y-axis value you have, it is simply going to half with every single half-life. So just keep that in mind. Okay? So these sort of three types of graphs that you should be aware of. And to find the half-life from any of these graphs, just take your original value, halve it, and see what time you are getting on the x-axis. So in this case, let's say I did not know that my half-life is actually 2 days. So originally I had 80 counts per minute in this case. I am simply going to halve it. When I halve 80, I get 40, right? So now I currently have 40. And I'm going to see how much time it took to reach 40, right? Because x-axis pe I have my time. So I'm going to go to 40, I'm going to do this, and I'm going to see what value I'm getting on my x-axis, and that is going to be 2, right? So that is basically how I found half-life through this graph. The same thing you can do over here. Your number of nuclei are originally 1,000, just half them, you get 500. You get this, and this is your t half, जो भी आपका x axis पे अभी उन्हें value नहीं दी हुई, but अगर value दी हुई है जो दी होती है, so you know how to find the value of that. So any questions so far? Anything you didn't understand?
Yeah, one thing that why does all the unstable nuclei have to half and turn into stable and then a half has to be unstable? Can't they all turn into the stable nuclei?
Basically, that's just a process, and that's just the property of radiation. It is a very random process that I personally, and I don't think a lot of scientists can answer that question. It's just a very random process, but we know from a lot of experiments that with every single half-life, half of them are going to be stable nuclei, half of them are going to turn into stable nuclei and simply, undergo radiation. So that's just a property of radiation that is just there. Okay, this is more or less the same thing that I explained earlier. With each half-life, the sample size you currently have halves. As time passes, the number of nuclei start to decrease, since due to emission of radiation, these unstable nuclei are now becoming stable. Since count rate is proportional to the number of unstable nuclei, the count rate also halves with each half-life. So we already know this. Now, this is an important formula that I want you guys to remember. And this is half-life equals the total decay time divided by n, where n is the number of half-lives that have occurred in the sample, right? अब हम actually देखते हैं how do we actually just apply this formula. So total decay time is simply the time in which you've been measuring the decays of a given sample. You've been measuring how many emissions you're getting from a sample. N, again, is the number of half-lives that have occurred in this given time. And half-life is just your half-life, the time taken for the number of sample to halve. Okay? So let's actually see how we can apply this formula. Half-life is equal to total decay time divided by n. Acha. Now, in most cases, you can find the number of half-lives by simply dividing the original count rate or the number of nuclei that they've given again and again by 2. Okay? So let's see how we're actually supposed to do this. Because आप लोगों के example से ही बेहतर समझ आ अच्छा. Now, a particular radioactive sample contains 2 million undecayed atoms. Okay? After a year, there is only 500,000 atoms left undecayed. what is the half-life of this material? Okay. Now, before we actually apply our formula that we've learned, well, we can't apply a formula right now because we don't have n and we have the total decay time because it said 1 year over here, right? Because it's experiment ke andar, we are doing it for a year. So we have the total decay time. Total decay time is going to equal to 1 year. What we don't have is we don't have the number of half-lives. So we don't have n, and we're also trying to find the half-life because that is the question. So currently we cannot apply a formula that we just learned because there are two unknowns. Now, what I just told you guys is that in most cases you can find n by simply halving the amount of the sample again and again. So let's see how that actually occurs. Now, if I originally had 2 million undecayed atoms, and after a year, there are only 5,000 left undecayed, what this basically just means is that my original radioactive sample was 2 million. Now I have 500,000. It really undergoed a certain amount of half-lives to reach this amount, right? Because it was decaying as time passes, and eventually it reached the 500,000 mark. So what I'm going to do is I'm going to start halving my amount of atoms to see how many half-lives it took me to reach this point. Now, this will make way more sense in a few seconds. Now, 2 million is basically just 2 into 10 raised to power 6. So I'm just going to write it like this. And I'm going to divide this by 2. Okay? The reason I'm dividing it by 2 is because after I divide it by 2, this tells me the amount of atoms left after a single half-life, right? Because with every single half-life, the atoms start to half, right? So if I divide this by 2, this tells me how many atoms are left after a single half-life. So if I were to do this calculation, 2 into 10 raised to power
1
6.
into 10 raised to the power 6.
Sorry, क्या answer है? 1 into 10 raised to power
1
6.
into 10 raised.
Exactly. So now you have 1 into 10 raised to power 6. But clearly this is not 500,000, right? Because, well, it's just not 500,000. The reason I need 500,000 is because I need to know how many half-lives it took me to reach 2 million to 500,000. So I'm going to divide this again by 2. Now, when I divide this again by 2, what do I get?
5 into 10 raised to the power.
5 into 10 raised to power 5 or 6?
Yeah.
5, right?
Yep.
Yeah. So after I divided it once again, 1 into 10 raised to power 6 raised to power 6 divided by 2, I get 5 into 10 raised to power 5. And this is exactly what I wanted. This is my sample size after a single year. So since I had to divide it twice, this tells me that this sample took 2 half-lives to reach this point. Does this make sense? Also, where is Alicia?
Yes.
एक second, let me just see Alicia कहाँ गई है. But this is making sense, right? Okay, it took me these many half-lives to reach the certain point, right? Okay. Now all I need to do is I need to apply my formula over here. So n हमें पता लग रहा है, and n is going to be 2 since it took me 2 half-lives to reach this point. Now it is a very simple case of applying our formula. Half-life is equal to total decay divided by n. Now total decay, I have
Is
1
it,
year. Sorry?
is it like decay को, do we have to always like check it in years, if it's in months, do we have to convert it or जिस तरह होगा वैसे ही use करेंगे?
I don't think you need to convert it, but it depends on the question as well. If they're asking it in years, oftentimes what they'll do is they'll already put it, like this is your answer, right? They'll already put something like years or hours over here.
Okay.
So in that case, you sort of have to stick with years. I'm going to be sticking with years in this case But if we had to just convert this into seconds or something, that shouldn't be that difficult as well, right? But abhi ke liye, I would say you can just stick with years, and 1 divided by, so basically the half-life is 0.5 years or half a year. Okay? So that was this question over here. Alicia, क्या I think पार्टी चली गई है? अच्छा, अब हम देखते हैं how do we actually measure radiation. So for measuring radiation, we actually just have two instruments that you guys need to be aware of. You don't need to know the ins and outs of these instruments. You just need to be able to see these instruments and know that their purpose is to measure radiation. So the first instrument we have is a GM tube or a Gieger-Müller tube, and the second is an ionization chamber. This is what a GM tube looks like. Over here, you have your radioactive source. In this case, it's cobalt-60. ये कोई emissions emit कर रहा है, and it is passing through this tube over here, and it is going through this GM tube. And this GM tube has a meter, and it shows you that there are certain amounts of readings on this. There is a certain amount of radiation on this. Okay. अच्छा. Secondly, आपके पास एक ionization chamber होता है, which sort of looks like this. Just be able to recognize this and see that this is used for measuring radiation. But usse aage you don't really need to know much about these. So just these are two instruments used to measure radiation. Be aware of them. Be aware of their names: GM tube, ionization chamber, and that's all you need to know for this. Okay. So a common issue with measuring radiation is the fact that there is background radiation in a lot of our readings, right? Now, background radiation is basically just the existence of radiation when there is no radioactive source near a measuring instrument. So if I were to, let's say, turn this GM tube on, and I have not brought this source near this, so I'm going to just cross this out. There is no radioactive source currently. But this GM2 is still giving me some sort of reading. It's saying that there's a radioactive source nearby. This tells me that there is a certain amount of background radiation or radiation from external places that I'm not measuring, but it is still affecting my readings. So that is just what background radiation is. It is the existence of radiation when there is no radioactive source near our measuring instrument. Now, this means that our radiation that is being picked up by our GM tube is actually coming from some source. We don't know what it is, but it is coming from some source. Now, typical sources of background radiation include, there are two types. You have your natural sources of radiation, and there are also your man-made sources of radiation. So in natural sources of radiation, background radiation, you have cosmic rays. These are rays that are developed in your solar system, and they come to Earth, and they can account for background radiation in a lot of cases. Secondly, there are underground rocks that have radioactive material in them. So naturally occurring, there are certain rocks that occur underground, and they can have radioactive material in them. They can have uranium, they can have other things, other minerals that are radioactive naturally. And when they emit their radiations, they can be picked up by our GM tube or our ionization chamber, and they can give us the background radiation readings that we are studying currently. There are also a few man-made sources of background radiation. There are nuclear plants that we have even in Pakistan, where the places that have nuclear weapon tests, there is a lot of radiation that is left behind by that weapon test. And there are also nuclear accidents that have, if they've ever occurred, an example is Chernobyl in Russia. These sorts of things basically just leave a lot of radiation in the background, and that can be picked up by our whatever measuring device we're using for radiation, right? So these are basically just a few sources of background radiation you guys need to be aware of, and you should be aware of natural or man-made resources. And yeah, Acha. Now an often issue with our background radiation is we have to subtract it from our readings, and the background radiation also affects our half-life graph. Now I'll actually show you how it affects our half-life graph. Half-life graph with background radiation. Yeah, so you can sort of look at it with this example, right? Now, this is a half-life graph, let's assume for any substance. And you can see that after a given amount of time, this, this sample basically just steadies at this 20 value of count rate. Now, the issue with this value and how I know that this is background radiation, the 20, is because after a given amount of time, let's say a large amount of time, my sample size or my count rate is eventually supposed to reach zero. The reason for that is after a certain amount of time, all of my unstable nuclei should be converted into stable nuclei. So by that logic, my count rate is supposed to be zero after a very large amount of time, right? But it is actually not. In this case, it is sort of steadying out at 20. Now, this tells me that this 20 is actually supposed to be zero over here. So this tells me that there is an existence of something that is, increasing the count rate in this case. So by that logic, I already know that my background radiation in this case is supposed to be something like 20, because this graph is actually supposed to reach to zero, but it's not. So this tells me that since it's steadying out at 20, it is sort of going like this. And that tells me that there is a 20 counts per minute background radiation present in my environment. I'll also show you how the graph is meant to be looking like. Yeah. So in actuality, my graph was something like this. There's a constant 20 background radiation existing. Sorry, not like this. There's a constant 20 background radiation that is already existing, and it is sort of supposed to look something like this. So it's actually supposed to reach zero, but since it's not, that tells me there is a lot of background radiation in the back. Okay? So just keep this in mind. They can oftentimes ask you this question, so you already know that this gap over here represents your background radiation. Okay? Achha. Now, in the given time we have, let's do a few uses of radiation, and then we'll call it a day. Now, in most industrial cases, radioactive sources are used to to basically just control the thickness of sheets, right? So you can have sheets of multiple materials. In this case, we're looking at aluminum foils. And what they do is they have a radioactive source on the top of the sheet, and they have a detector on the bottom of the sheet. And this radioactive source is a beta source. So it emits beta rays that pass through this aluminum foil. Now, the detector on the other side just measures how many beta rays are basically coming through the aluminum foil in this case. So let's say in a given time, there are about 3 to 5 rays that are passing through this aluminum foil. Now, if the sheet accidentally, while this entire aluminum foil is being made, if the sheet gets thicker, what is going to happen is more of the beta rays are going to be absorbed by the aluminum foil, which means that it is going to lead to a smaller reading on the detector, right? Likewise, if the sheet accidentally gets thinner, right, what is going to happen is more beta rays are going to pass through the detector, and since you have a thinner sheet, less of them are going to be absorbed by your sheet over here. What this leads to is that the detector is going to show a larger reading. Now, since you already know that if the sheet is going to get thicker, the detector is going to show a smaller reading. If the sheet is going to get thinner, the detector is going to show a larger reading. Since we already know all of these things, we can make very quick adjustments to the thickness of the aluminum foil so that the thickness is sort of uniform. It stays the same as time passes on. So this is one of the bigger uses of radiation. It is just controlling the thickness of a certain sheet with the use of radioactivity. So you have a certain fixed amount of radiation that you want in the detector. If it starts to, lie out of that range, let's say it goes above that range, or let's say it goes below that range, you can make very quick adjustments to the thickness of the aluminum foil and, make those adjustments. Okay. So any questions with regards to this?
No.
No? Okay, sure. And if this class ends, just no need to rejoin. That's completely fine. Acha. Now, the reason that we use alpha particles instead of beta particles is because alpha particles would be very easily absorbed, whereas gamma rays would be very easy to, they would just pass through this aluminum foil like this.